Okay, all right, ladies and gentlemen, boys and girls, children of all ages, this talk is called Python's infamous GIL. It is about the GIL. It is about the history, the problem that we had, how we're solving the problem, the ramifications of that solution, how it's affecting us still today, and how the GIL might change in the future. We start in 1992. In 1992, Python was 2 years old. It was still young, it was fresh, it was a vibrant community. It was mostly used inside of CWI, but it had been released on the internet. And Python had this lovely C API that made it very easy to add new functionality to it. So people were adding new things all the time. People wanted to experiment with new technologies by adding them to Python and seeing what they were like. And there was this new technology that was looming on the horizon. It was called threading. Threads were like processes, but inside of the same process. In classic Linux or Unix, you'd have a process and you'd call fork, and that would make a clone. So now you'd have two processes that actually had all the same state, all the same memory. They were doing the same thing. But one was a child and one was the parent, and they sort of diverged from there. And they were in two separate memory spaces. Threads were like that, but without cloning the memory space. So you'd have two things running inside of the same process at the same time, which meant that they could communicate directly through memory. This was a kind of an exciting technology. Everyone was adding it. It was already supported in SunOS. They called it lightweight processes. The new operating system from Microsoft, they called NT. That was in beta, and that had threads. It would be a couple of years before Linux added threads, but they were working on it. Now, keep in mind, this is 1992. You didn't actually have multiple CPUs inside of a computer, or at least most people didn't. It was rare to see. So you would have one CPU, one core, but you could divvy up the work. You could sort of time slice and seemingly get multiple things done at the same time. And people wanted to do it in Python. But you can't just create new threads and expect everything to work right away. Threads are going to cause problems. First of all, Python used a lot of global variables inside. Python's written in C, of course. In C, what we call a global variable in C is roughly equivalent to a module attribute in Python. So there's only one of them, and everyone can find it. And you can imagine if you had multiple threads trying to interact with a module attribute, if they both tried to change it at the same time, you might have problems. Even more fundamental, Python uses something called reference counting to manage the object of a lifetime, to know when an object is no longer needed and it can be destroyed and the memory given back to the operating system. And that caused a real problem for threading. I'm going to go into a lot of depth on reference counting starting right now. So reference counting. This structure is at the top of every object inside the Python runtime. You can think of it as the core class, the object class, and everything has to inherit from it, although C doesn't actually have inheritance. So the second thing is the type of the object. That has an enormous structure that has all sorts of information about the object in it. And this first thing is called the ref count. That is an integer, and that is a number that says how many people have references to this object right now. Managing the reference count of an object is very important. Python has these two built-in what are called macros. They're kind of like functions, but it's sort of a textual substitution. So this incref and this decref, these increment and decrement the reference count on an object. You'll notice decref is a little more complicated. What it's saying is, take the reference count, subtract 1 from it. If that number is now 0, we're going to call delref, which turns into calling dunderdel, effectively, and then giving the memory back to the operating system. So this is what it looks like from the Python world. Let's say that we have this line, we create a new empty list, and we assign it to A. So we have this object, which is the empty list, and we have a reference to it. A has their reference, and the reference count inside the object is now 1. If we have a second line, B equals A, that's going to do the same thing, but now we have to bump up the reference count to 2, because now 2 people have references to this object. There's actually a way that you can inquire about the reference count of an object in Python. It's called sys.getRetCount. And if you pass in A, in this circumstance, of course, you get 3. The reason is A has a reference, B has a reference, and you create a new reference when you pass it into sys.getRefCount. So that's all working fine. That's reference counting. Now let's talk about reference counting when it deals with threads. This gets very complicated very quickly. So I'm going to show you what this looks like. I'm going to show you what's called a race condition between these two threads. We have two threads, thread 1 and thread 2. They're both going to try and decref. They're going to try and drop the reference count on a shared object they both have a reference to. I'm going to show you twice, once where it works, and then the second time where we hit the race. So first of all, let's expand the C code. That decref is actually kind of a function call. This is the code underneath. But actually, we can't even look at this level. The problem occurs at the CPU level, and in order to really understand it, we need to look at the assembly language. It's not terribly complicated assembly language, so I'll be real gentle, but this is the level we have to look at in order to really understand the problem. So let's say that object has a reference count of 3. This, again, the first time it's going to work. So we load the reference count into AX. AX is kind of like a variable inside of the CPU. It's what we call a register. So thread 1 has an AX, it's the value of 3. We decrement AX, it's now 2. And we store AX back into the reference count on the object. The reference count on the object is now 2. The second thread comes along, does the same thing. Loads the reference count into AX, decrements it, stores it back. The reference count is now 1. I will remind you, we had an object. Its reference count was 3. 2 threads came along that were holding references. They both dropped their references. The reference count is now 1. That worked. Let's do it again. But this time, it's going to fail. Same code, just run in a slightly different order, where we lose the race, quote unquote. So thread 1 comes along, loads the reference count into AX. AX is now 3. Thread 2 does the same thing at about the same time. So now we load AX, and AX is 3 over here, too. We decrement, we decrement. We store, we store. The reference count is now 2, but both threads are done dropping their reference counts. The reference count in this object is now permanently 1 higher than it should be. That's a bug. And what happens when the reference count is too high like this is that this memory is going to be lost. This is, eventually the last person is going to drop their reference, but the reference count will still be 1. The memory will never be reclaimed. The dunderdel will never be run. This is a leaked memory reference. The opposite thing, if you had a race during the incref, that's even worse. That would mean that the reference count was permanently 1 number too low, and that meant that when the last person, the next last person was coming along, the reference count is 2 and they drop it to 1. Well, it would be 1 too low, so it would be from 1 to 0. When the reference count hits 0, we call dunderdel, we free up the memory and give it back to the operating system, but we still have somebody who has a reference to that object. Terrible things happen at that point. If you're lucky, all you do is crash. If you're unlucky, then it still accesses the object, which may have garbage values in it, and you compute something terrible, and now goodness knows what sort of undefined behavior you're in. So we have to solve this problem if we're going to have Python, which is using reference counting, be able to run multiple threads. So the classic solution to this is to add locking. And the straightforward solution would be, well, let's add a bunch of locks to Python. Let's add a lock around like every global. A lock, by the way, is it's an object that only one person can have. Only one thread can hold at a time. So if 2 threads want to access a lock, one of them succeeds and grabs it. The other one has to wait. So if you have a lock around a global variable, then only one person can access it. That means that you're not going to have these race conditions anymore because you're going to serialize access using these locks. So we could have 1 lock per global, or we could have multiple locks, or 1 lock for a set of globals or something like that. And most importantly, we could have a lock around reference counting. But having multiple locks like this leads to another problem. It turns out threaded program is very complicated. This is a classic problem in threading called a deadlock. Let's say that we have 2 threads, thread 1 and thread 2. And we're going to have 2 locks, A and B. Both threads happen to want to use both of these locks. And the problem is that they use them in the opposite order. So thread 1 acquires A, then B. Thread 2 requires B and A. And again, if things happen in the right order, then we're going to have a problem. And I'll show that to you right here. So let's say that thread 1 comes along. It says, I need lock A. Nobody's using lock A right now. You can have it. That's fine. Thread 2 comes along and says, I need lock B. Well, nobody's using right now. You can have it. That's fine. Now, thread 1 says, I need lock B. It attempts to acquire it, but it's being held by somebody else. It has to wait. Thread 2 then comes along and says, oh, I need lock A. But thread 1 is holding it already, so it has to wait. These 2 threads are now deadlocked. They are now permanently locked. They cannot make any progress forever. So Guido did something very clever. He introduced something called the GIL. This was in 1992. This was the check-in. And among other pieces of code that he touched, he added this 2 lines of code to PyC eval. This is the GIL. It is a single lock that you hold in order to so the rule is, in order to interact with the CPython interpreter in any way, in order to run bytecode, in order to talk to a Python object, in order to make any function call into the CPython API, you have to be holding this lock. That's the rule. Now, this was 1992. You want to see what it looks like today? Boom. This is the 2.7 GIL. It's exactly the same. They just changed the name on the type a little bit, and they added a comment because people want to know where the GIL was. So here it is. Now, there are a lot of ramifications from this design. Fundamentally, I would say this is a wonderful design. This design was simple, and simple means easy to get right. There are some things that are kind of complicated about the Python C API, like reference counting, for instance. The GIL is not one of those things. It's dead simple to get right. Nobody had any problems understanding it. It's a very simple rule. You want to do anything with the Python interpreter, you have to be holding the GIL. That meant that everybody got it right. One lock means you can't have any deadlocks. Again, very good design. Now, how does this affect programs that run under Python? Well, if you have a multi-threaded program that is I/O bound, you really don't have a problem. And I'm going to show you why on the next slide, I think. So I/O bound is OK. But as everybody knows, a CPU-bound program that runs under Python is effectively single-threaded. And I'm going to talk you all the way through this. So let's talk about why I/O bound programs are OK under the GIL. So an I/O bound program, what it's really doing is it does a little bit of computation, and then it says, I'm done computing. I need to wait on file I/O, on writing to a file or reading from a socket or something like that. So it does a little bit of work, and then it waits for a long time. It does a little bit of work and waits for a long time. If you have multiple threads that are doing this, well, one of them runs, and then it's done, and it's just waiting. That allows the next one to run. And that allows the next one to run. So a lot of threads can share the CPU no problem. And that means that in CPython, they can share the GIL no problem. And the way this actually works underneath, there are these two macros, begin allow threads and end allow threads. And what you're supposed to do is, in the C API, they say anytime you're going to go and do a lot of work, you're not talking to the CPython API at all, you're not talking to any objects, you're just doing something else and it's going to take a while, you should drop the GIL, and this is how you do it. So begin allow threads drops the GIL, it releases the lock, allows other people to grab the GIL and use the CPython interpreter, and then you do whatever work you're going to do in the middle. And then when you're done doing that work and you need to talk to the CPython interpreter again, you call this end allow threads, which reacquires the GIL and allows you to proceed. So what do you do in the middle? Well, sleep, for instance, that doesn't need to talk to the Python interpreter. Talking to a file, like reading or writing from a file, or reading or writing from a network socket. All those things, everybody always religiously drops the GIL before they do it, and they pick up the GIL afterwards when they're done. And that allows I/O-bound programs to share the GIL very effectively. But if you have multiple threads that are all trying to do computation at the same time, where they're all trying to run Python bytecode, they all want to have the GIL. Only one of them can have it at a time, so that doesn't work. This is the classic problem that the GIL gives us in multi-threaded programming. But it was even worse than that. So there's a guy named David Beasley. He's a computer programmer. He was a physics professor for a while, I think, in Chicago. And he gave a talk to the Chicago area Python user group called Understanding the Python GIL in 2009, where he showed that actually, so people had been assuming, yeah, the GIL's fine, and they just like ignored it and went on with their lives. It turns out the GIL was actually really terrible. So there's something inside of CPython called the check interval. This was a number, and originally it was 10, and then they changed it to be 100, which was less aggressive. And what this number meant was, this was the number of bytecode instructions that you were supposed to go before you checked and saw if somebody else wanted to run. And if somebody else wanted to run, you were supposed to release the GIL and let them run. The idea here is if you have, let's say, 4 CPU-bound threads running inside of Python, you should run them for a little while and then let the next guy run, and then let the next guy run. And you should sort of share the CPU and let them swap back and forth at an interval of like 100 bytecode instructions. David Beasley discovered it was much longer than that. So what this graph is, this is 2 CPU-bound threads running on a 2-core computer, and both of them attempting to share the GIL. Green sections are, I have the GIL and I'm running. Red sections are, I am waiting for the GIL. This interval that he called out is 66,700 ticks. That's 667 times longer than it was supposed to run at a time. So the GIL was not being given up on anything approaching a nice, discrete, granular level. Yeah, there was another problem. Let's say that you have 2 threads, and one of them is CPU-bound. So it wants to be holding the CPU, wants to be running bytecodes all the time. And the other one is I/O-bound. So it runs for a little bit, and then it's done, and it waits for a long time. What you want is you want the CPU-bound one to run whenever it wants to, except when the I/O-bound run is ready. If the I/O-bound thread is ready, you should let it run right now, because it's only going to run for a little bit, and then it's going to be done, and it's going to be waiting for a long time. That keeps the I/O-bound thread happy. And then the CPU-bound thread gets all the rest of the time, it's happy too. This maximizes happiness inside of the process. What you don't want is for the CPU-bound thread to run forever, and the I/O-bound thread says, hey, I'm ready to run, and it has to wait for a long time. Well, guess what? That's what was happening in CPython. This green thread was CPU-bound. This top thread, I think the white means I'm not doing anything, I don't care, but the red part was I'm waiting. And waiting is bad on I/O-bound threads. This is exactly what you didn't want. This is a term, the term for this in scheduling is called priority inversion, where you want this one to have higher priority than this one. This is I/O bound and this is CPU bound, and what was happening was the reverse. This is also called thread starvation, where the thread is being starved for CPU time. So to address these problems, discovered by David Beasley, oh, that's right. So let me show you why we had the problem. Here is the code that actually happened for a sysget check interval. What it really is, this pi thread release lock, that's give up the GIL. And then this pi thread acquire lock, that's re-grab the GIL again. It's just like the other thing, where we release the GIL, and then we go off and do something for a while, and then we reacquire the GIL. But guess what? Here, we don't do anything. This is, oh, it's been 100 time secs. We need to release the GIL and let other people run. Well, guess what? We release the GIL, then we grab it immediately. We release the GIL, then grab it immediately. This literally is like nanoseconds. And if the other person happens to grab it at the exact moment that the lock has been released, then they get to run. Otherwise, they miss it and they have to wait again. That's why, once out of every 667 tries, the other thread got the lock. So this was kind of a problem. So the solution for this was what was called the new GIL. This was done by Antoine Petrou in 2009, after, obviously, David Beasley announced his research. And what he did is he added this other variable called GIL drop request. This is a flag. If you attempt to grab the GIL and you fail because someone else is holding it, you set this flag to true. And the next time they say, oh, it's time to release the GIL, they're not allowed to reacquire it until somebody else has grabbed it first. This shipped in Python 3.2. This has not been backported to 2.7. I don't think it ever will be. Now, this solved a lot of the problems with the GIL, but it didn't solve all of them. David Beasley can still torture the GIL and make terrible things happen. But this is considered sufficient for most workloads. And in order to really solve the problem and really do a good job of solving priority inversion and thread starvation, what you're really talking about is a full-on scheduler. And that seems like killing a butterfly with a machine gun. It would be a very complicated piece of technology to solve what is a relatively simple problem inside of CPython. Now, I'll remind you, Python was developed back in the days of the single-core computer. But the world has sort of changed around us. So back in 1990, we have the development of Python. Then we fast forward a bunch of years, 2005. 2005 was the year that computers really started to go multi-core. So there were multi-core computers earlier. I had one in like 97 or something like that. But you had to go to a lot of work and to get it, and it was pretty rare. But it was in 2005 that server CPUs and desktop CPUs and game console CPUs all sprouted a second core, or even multiple cores beyond that. That's when multi-core computing really took off for the user. 2007, laptops went multi-core. 2011, tablets and phones and even embeddable systems on a chip all went multi-core, very small CPUs. In 2013, eyeglasses went multi-core. In 2014, wristwatches went multi-core. Ladies and gentlemen, we live in a multi-core world, and CPython is ill-appraised to take advantage of it. Because, as I say, if you want to run CPU-bound task threads around multiple cores, you just can't. Now, Guido has addressed this many times. He had an old blog on Artima. In 2007, he said, I'd welcome a set of patches into Py3K only if the performance for a single-threaded program and for a multi-threaded but I/O-bound program does not decrease. This is a very high bar, and nobody has been able to meet it yet. Back in the 1.4 days, there was what was called the free threading patch. What this did was it allowed Python to run on multiple cores at the same time. First of all, to address the globals, it took all the globals and stuck them into a structure, which is the C equivalent of a class. So all those global variables became class variables, and now you could have multiple instances of those classes. Now you can have multiple, one per thread. He also added a mutex around the increment and decrement. So there was a single lock that you had to hold in order to incre and decre. This was great because it didn't change the API. Everybody's extension still worked. The problem was performance was terrible. It was between 4 and 7 times slower. This is according to David Beasley's revival of this patch to examine if it was viable at all. The answer is no. There's another thing that we could do here. So Antoine Petrou, a couple of years ago, there's a special instruction that's on modern CPUs. All of the CPUs support it these days. I doubt that Python runs anywhere that doesn't have one of these instructions. It's referred to collectively as atomic incre and decre. What it is it's an instruction that says, take the value that's sitting in this memory over here and add 1 to it in such a way that there's guaranteed no race conditions. You can have 4 cores, 8 cores, doesn't matter. It's guaranteed that it will be incremented properly and there cannot be a race. This worked. He got this to work pretty well. It didn't change the API, and it was only 30% slower. And I say only because that sounds fantastic. It still doesn't meet the bar that Guido is demanding, but it's only 30% slower. But let's talk for a minute about all of the Python interpreters in the world. The CPython interpreter written in C is only one of 4 major interpreters, I would say. There's also the Jython, IronPython, and PyPy. And of those, CPython is the only one using reference counting. The others use what's called pure garbage collection. CPython is the only one with a GIL. The other ones don't have a GIL. PyPy kind of has a GIL that's used during garbage collection, but it's a lot more multicore friendly than CPython is. So pure garbage collection seems like it would be a good way to go to get rid of the GIL, and it would be. The problem is that it would incur massive API changes. It would break every single C extension guaranteed. They would all have to be rewritten a great deal in order to support garbage collection. This breaks everybody, and I'm not sure that we can really do it. And if we did, we'd have to call it like CPython 4.0. Would it be faster? Would it be slower? The answer is, well, we don't really know. We wouldn't know unless we actually did it. The conventional wisdom around garbage collection is it's about roughly equitable with reference counting, which is a good sign. But again, we wouldn't know unless we did it, and it would be a massive amount of work in order to find out. But also consider this. Of those modern languages that have pure garbage collection, none of them support the C API. This is really the fundamental problem why we can't switch to garbage collection is because we have the C API. In order to have a C API, you have to deal with objects. In order to deal with objects, you have to understand object lifetimes. In order to understand object lifetimes, you have to understand the internal memory management API that's used by the program, which means that Python had to expose its garbage collection to the rest of the world, which made it part of the API, and that means we're stuck. We can't change it without breaking every C extension out there. So what these other VMs did is like they don't have a C API at all. Instead, if you want to call into a C library, you do it from inside of the language, like with a JNI or a CFFI or something like that. So in my opinion, all we can do here is if we have a C API, then that means exposing our memory management to the world. If we went to pure garbage collection, we break every extension out there. And I would say at that point, this is such carnage that we should really probably get rid of the C API and encourage everybody to rewrite their extensions using CFFI in pure Python. And I don't think we can get away with that. So oddly, I don't think that this is something that we can ever change about CPython without just driving all the users away. The only possible way that we could get to multicore-friendly Python, CPython, without breaking everybody is with atomic anchor and decker. And my guess is if somebody ever gets rid of the GIL, they're going to be doing it that way. That's it. Wow, look at that. I didn't think I was having time for questions. Ladies and gentlemen, that's a land speed record. I've never done this talk under 30 minutes.
Okay, I think we have a few minutes for questions. So if
yeah.
anyone has a question,
if you're not all stunned into
wave your hand,
silence.
I'll wander around.
Computing power is always increasing. Do you think that at some point the decision will be made that the 30% drop in performance might make it worth implementing, for example, the atomic anchor and decker?
So between you and me, I think that we might be able to meet Guido's requirements if we said, here's a way that you can build Python one of 2 ways. This way has atomic anchor and decker, and it's 30% slower. This way doesn't support threading at all, and it's just as fast as the old one that you cared about. If you don't care about threads, use this one, and that gives you the performance that you need. If you need threads, guess what? This one's going to be better for you anyway, so you use that one. So I think we can make everybody happy by doing that. To answer your question more generally, what I would say is that, so first of all, not every workload deals well with threading. There are a lot of workloads that are just like start at the beginning and do all your work and end at the bottom. If you have what's called an embarrassingly parallelizable program, yes, you care about threading and you want to have it. Most people, a lot of people in this room, I guess, probably don't have workloads that are all that friendly to multi-threading, and so they really don't want to see single-threaded performance hurt. So, but I think that as computers become increasingly multi-core, and believe me, they're going to, it's getting so hard to make the CPUs themselves faster, but it's really easy to take this thing on the silicon and make another one right next to it. So adding cores is pretty easy, and they're just going to keep doing it and doing it and doing it. More cores is going to be the standard in the future. And in order to take advantage of all of the things that your hardware supports, you're going to have to try and force your problem into a multi-core solution so you can take advantage of all of the CPU processing power that is offered by your computer. So it's increasingly, there's going to be increasing pressure, I think, to make Python multi-core and to make your program multi-core friendly and to solve your problems that way. I think there was an answer to your question somewhere in there. OK.
Is the answer to switch to PyPy and ditch CPython completely?
So, like I said, PyPy kind of has a GIL. They say they're a lot closer to being able to get rid of it than we are. I would say that if there was a lot of interest in switching from CPython to PyPy, then people would be doing it because they could do it today. Because they're not doing it today suggests to me that there isn't that much interest in doing it. In as much as we have all this pressure from taking advantage of multiple cores and things like that. There are a lot of trade-offs involved with PyPy. PyPy is getting better all the time. Startup performance is still slow. Runtime performance is slow until you hit the JIT, in which case it speeds up a great deal, of course.
Just to point out that a lot of people are beginning to use PyPy, particularly in the finance industry.
Oh, good. That's fine. Doesn't hurt my feelings. Fundamentally, PyPy, so CPython, one of the things that's really wonderful about CPython is that it's dead simple to work on. CPython internally, very clear code, very simple architecturally. Someone who is familiar with C can get up and running hacking on CPython relatively quickly. PyPy is mind-numbingly complicated internally. And they don't have very many core developers. And they're not getting a lot more. And I'm not looking forward to ever hacking on PyPy because it is so crazy complicated internally. I think that there is a lot of call for having a simple reference implementation of Python. And as long as CPython's performance is anywhere near competitive, I think that people are going to continue to stick with CPython. Because I will point out that PyPy is still lagging behind. They're talking about 3.2 compatibility with 3.2, and meanwhile 3.5 shipped on Sunday. So they really are pretty far behind, just like all the interpreters are behind. So again, if you want to run the freshest Python, you're going to run the reference implementation, which is still CPython. I don't see it changing anytime soon.
Very short question about the Inker-Decker atomic overhead. You said 30%. Was it identified where that 30% was? Are those instructions slower, or is it the overhead of scaffolding around it?
So fundamentally, in order to guarantee that atomicity of those instructions, things kind of have to come screeching to a halt. You need to do a certain amount of coordination. I mean, I've never designed a CPU, but I imagine that there's a certain amount of coordination internally between the cores, and it might be as bad as something like a pipeline spill, where we're doing a bunch of work speculatively in the future, and now we can't guarantee that because this memory changed and we have to throw it all away. So it might be like a pipeline spill on all of your cores. I don't really know what's going on underneath, but it is fundamentally the instructions themselves are slower than a direct Inker and Decker that's not guaranteed safe across cores. Mr. Van Lindbergh.
What about Eric Snow's idea of trying to basically have an interpreter per thread, and then limiting per inter-thread communication? Right.
So the answer to that is that that really doesn't buy you anything beyond what multi-core already buys you. If you have them completely divorced from each other, then you have all the problems that you have with the multiple cores, the multiple processes right now. You can't communicate directly without serializing. Maybe you can use shared memory, but you can already use shared memory across processes. Some people have said, like Armin Ronacher has said, that's all he cares about. That would get him. And if we did that, that wouldn't cause any API changes. We could hide all those changes inside. We could hide the fact that we'd have to take all the globals and stick them into structures. And then we could hide a reference to that structure inside of what's called thread local memory. So all the threads would have their own reference to it. The APIs wouldn't have to change. But I don't think it really buys you much of anything. If there is a problem that solves, I'm not aware of it.
Okay, I'm really sorry we've run out of time. So if you just say a big thanks to Larry.